Hello class, in this video we're going to look at lesson 7.5, a triangle hierarchy. We haven't done much geometry in 5th grade this year, very little, and there's not a lot left in it. We used to do a lot more with geometry, measuring angles and whatnot years ago before the state made some changes. So if this one seems a little confusing or you're kind of clueless, well, don't worry, it's because we really haven't done much of it this year and you're not in the class here with me. To be able to ask questions. So hopefully the video will help explain everything. And if you do have any questions afterwards, feel free to shoot me an email. All right, so what we're going to do on this page, and this page is really going to go with the next page as well, but once we get this page up, the next page should go pretty smoothly for us. So just like always, we're going to work through this. If you feel like you understand what's going on, hit pause, try it on your own, then unpause to watch the rest of the video to see how you did. And remember, if there's anything that really doesn't seem right, and again, I've made mistakes, you're just not here in class to catch it anymore when that happens, don't sit there for a half hour trying to make head or tails of whatever it is I've done or said. Just email me, let me know that you think there's an issue. That's not going to be a problem. I'm not perfect. We all know that. All right, so here we go. On the left, write the categories and subcategories from the triangle hierarchy you create in class. Well, I'll be doing that part. Use the hierarchy to classify your triangle cards. When you are finished, glue or tape the cards in place. So this is where you need this page. So that was, I think, the first page of the math materials underneath the cover letter that you either got in your paper packet or that was sent to you electronically. So what we're going to do here is we're going to look at all of these triangles. We're going to try to come up with a category for them and some subcategories based on things that we see. And we're going to focus on the lengths of the sides. So if you haven't had a chance to look at these yet, you might want to pause the video. You can either look at them on the screen or go grab your sheet. All of these are triangles. They're all three-sided shapes. So when we look at the book, we see where it says triangle hierarchy. So that's what we're going to start with. We're just going to write triangle. And then we would tape, glue, or if you don't have any of those things, just try to draw all of the cards on that sheet of paper that are triangles. Now, we're not doing that part yet because we are going to come up with some subcategories, things that we notice that some of the triangles have in common that maybe they don't all have in common. So once we start making these other subcategories, we're going to take all of those triangle cards and we're going to start pulling them down into these new subcategories. So whatever's left over will stay up here. All of those shapes were still triangles, but some are going to filter down to subcategories. All those triangles are still going to be triangles, but they're going to be special in some way, which is going to bring them down to the next level. Kind of like all of you. All of you are 5th graders, but if we wanted to, we could subcategorize those as those with long hair, or short hair, or girls, or boys, or whatever. So first thing we're going to do is take a look at our sheet to try to get an idea of some things that we notice. And again, this is where you might need to pause the video. All of these are triangles. They all have three sides. But if we wanted to try to figure out if there was anything unique about some of them that maybe is not unique about all, we might notice that there are some symbols on them. Like this triangle has a tally mark on each line. This one has tally marks on 2 of the lines, but not on the 3rd. This one had them on all 3. This one has them on all 3. It has 2 tally marks on each line. This one has a 90-degree angle. This one here doesn't have any tally marks on any of the lines, nor does it have any right angles in there. So when we look at these, we might first start asking, well, why do some of them have tally marks? So if we look at this triangle here, each line has 1 tally mark on it. Why do you think that is? This one, each line has 2 tally marks. Do you see anything similar about those 2 triangles? And if you think you do, well then let's look at this triangle. It only had tally marks on 2 of the sides, not the 3rd. And then we have this one over here that has different tally marks on each side. So if you looked at this long enough and you really compared these, cut them out, move them around, maybe even overlap them so you can kind of see through to see how they match up, you might notice that this triangle and this triangle are the same. So why the different tally marks? The different tally marks doesn't really matter. You might think, oh, maybe this line is twice as big as this one. These are really two different triangles. All this means is whatever the measurement of this line is, it's the same as the other two lines because they have the same tally marks. So this line is the same as this one, same as this one. Over here, this one has two tally marks, so it's the same length of any other line in this triangle with two tally marks. Again, it does not mean that this line is the same as this one, two different triangles. Now, when we looked at this one, it had three different tally marks. If we measured, this line is not the same length of either of these, so they're all marked differently. Well, then how come some of them don't have any marks at all? Well, in those, this would mean simply as the default, none of the lines are the same length because they did not give us any notation to let us think that they were. This one, you might wonder, well, then why did they do it for this one? Well, I guess if you were looking at this kind of quickly, these two kind of look the same. They're pretty similar, but they are not equal. So marking these just kind of makes it easier to see that they are not the same. But we have a whole bunch that don't have any marks at all. If there are no marks at all, even if two lines might look similar in length, they are not. Any that are have tally marks to show it. These two lines both have two tally marks. These two have the same measure. And then again, you have the ones like this over here that look kind of close. So they're kind of helping us out by saying, you don't need to measure. We're going to tell you. Some of them, it should be obvious that they're not the same. We're not going to mark those. All right, so now that we've looked at these, we can see that some of our triangles don't have any sides that are the same length. And there's others. You can go through and look at them. And then we do have some that have all sides the same length. And then there are some that just have two sides, like this one. So what we're going to do is we are going to subcategorize all of these triangles into two other categories or subcategories. So the first one we're going to do, and that's where I'm going to need to start writing on our book, so hopefully you have your own sheet handy somewhere. Now let's get that out of the way. So first off, we're just going to start with triangles for our main category. And all of those shapes on that sheet were triangles. They would all go here to start with. But we're going to subcategorize. Not really sure how far down to draw my line here, but again, you can fiddle with this before you tape any of your things down there. All right, so for my first subcategory, I'm going to start the triangles that had two equal sides or more, because there were quite a few that had two or three sides that were equal. Those get a special name. They are called, oh wow, if this is as good as I'm going to write today, I feel sorry for all of you. And again, I can't really erase, so let's try that again. So these would be isosceles triangles. And please spell triangles right. It's not ELS. They're not triangles. So isosceles triangles, these are the triangles that have, and I'm just going to put this in parentheses, at least two equal sides. They can have more. They have to have at least two. And now if we go back and look at our sheet and try to find all the ones that have two sides with the same markings, we will see that in that top row, no, that one has 3, so that one would go into this new category. No, 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 no. This one has at least 2 that are the same. This would go into that new category. This one has at least 2 sides equal. It would go into that new category. Then let's see. We get down to the last 2 rows. No. This one has at least 2. No. This one has 2 that are the same length, so that would go into that new category. No. No. This one has 2 that are equal, so that would go in. And no. So all of these triangles would have originally been in that very, very top part that just said triangles. That part way up here. But we now have found some that are special triangles. They have at least 2 equal sides. So those cards that would have been up here that we just looked at that had at least 2 equal sides, 2 or 3, we would pull them out, and they would now go down here for isosceles triangles. And when we were looking at the triangles, we noticed one other thing. Some of the triangles, not this one only had 2 equal sides, but some of them had 3 equal sides. So some had more than 2 equal sides. All of their sides were equal. So this is going to be our last subcategory. So if you are an isosceles triangle, there is a chance that you might also be an equilateral. You can kind of hear equal. Lateral means the sides, so equal length sides. And I'll just put in parentheses 3 equal sides. So not all of the isosceles triangles had 3 equal sides. Some just had the 2. But some of those ended up having all 3 that were equal. So go ahead, pause the video, take your shapes, and again, if you need to just draw them in the right spots, draw them where they would go. I would start from the bottom. All the ones that had 3 equal sides, tape them, paste them, or just draw them down here to the best of your ability. Put the markings there in case you forget why you thought a certain one was an equilateral triangle or an isosceles. And by the way, for equilateral, you kind of hear the word equal, all the sides are going to be equal. This is a trick I learned when I was a kid. Maybe it helps you. Isosceles, you have 2 eyes, so it has at least 2 equal sides, if that helps at all. And not that we're doing it on this particular page, but if you wanted to know, well, what about the triangles that don't have any equal sides? Do they get a special name? They actually do. It's called scalene. And I always thought of that one as scales. Generally, creatures with scales aren't considered the cutest creatures. And those triangles, since they don't have any symmetry, generally are probably not considered the pretty triangles, the ones that you would typically think of when someone says the word triangle that comes to your mind. So anyway, if that helps you remember the different terminologies, go for it. If they don't help you, then sorry. All right, so anyway, equilateral triangles. Try to draw all the ones that have 3 equal sides first. Then back it up a step. All the ones that you haven't already drawn down here that have 2 equal sides. Because again, if they have at least, they mean they have to have 2 or more equal sides. We've now pulled out all the ones with 3 equal sides down here. So whatever's left over here of the ones that have just 2 equal sides would go here. But don't be confused. Equilateral triangles are still also called isosceles triangles. Just as both isosceles triangles and equilateral triangles, when we go back up to the top, those are all still called triangles. So then whichever triangle shapes that you have left that you have not filtered down into the subcategory for isosceles or equilateral, whatever is left over gets put up here. So I'll give you a few seconds to pause the video, do this part on your own, and then I'm going to put up my final answer page up there so you can see how you did. I'll give you 5 seconds to pause the video before I put the new sheet up. All right, hopefully that was enough time. So here is the new page, or my page, and I guess I need to get rid of all of the writing. There we go. So I'll start at the bottom, originally all of the cards would have started here. They were all triangles. Some became isosceles, meaning they had 2 or 3 equal sides, and then some of those got filtered down even farther to all 3 sides equal. So once I did all of that, at the very, very bottom, I only had 3 triangles that were considered equilateral. And we can see this one has all 3 of the same markings, this one has all 3 of the same markings, this one has all 3 with the same markings. So there's my proof or evidence that these were in fact equilateral triangles. I wasn't guessing. I didn't say, well, this one kind of looks the same. They're giving me those markings to show me that those are equal. And if you turned yours a different way than I did, don't worry. It's as long as you find those 3, however you rotated them when you put them in your book or drew them is fine. All right, so now backing up, there were 3 triangles that were still left over in the isosceles triangle subcategory. And we can see only 2 of the lines have the same marking. The third one doesn't have any marking, so it does not match. This one, 2 of the sides had the same markings, third one does not. And then same thing here. Now remember, all of these down here were up here. They were isosceles triangles. All of these equilateral triangles did have at least 2 equal sides, meaning at least 2 of these sides were the same length or more. They were more. They had all 3 equal. But again, equilateral triangles are a subcategory of isosceles, which means they have the same traits as isosceles triangles. Both of these are subcategories of triangles, which means they have the same characteristics of triangles, the 3-sided shape. So up here now are all of the triangles that are left over that we could not subcategorize as either isosceles with 2 or more equal sides or equilateral, all 3 sides being the same length. So it looks like I have, 10 left over? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So hopefully you had these 10. And remember, different markings. All 3 of these sides were different. Same with this one, 3, 2, and 1. And then the ones with no markings is because none of the sides were the same length. They tried to do the markings on ones that you thought maybe could have looked tricky. Like this line and this line look like they're about the same, but they're telling us no, they're not. If we measured them, they would be off a little. So again, should have 10 that were left over just as triangles, 3 that end up getting stuck in the isosceles triangle subcategory, and then 3 that filtered all the way down into the subcategory for equilateral triangles. So if you don't have this, please get this in your book. Again, whether you have to draw it or maybe you just move the pieces around if you were able to cut them out and move them into those 3 separate piles, because we are going to use these to answer the next page. So I'll leave you a couple seconds where you can pause the video, make sure you have this right in your book or get it there, and then I'll move it down to each of the next subcategories, and then we'll move on to the next page. So pause the video if you need to now. Okay, here are the last 2. So again, pause the video if you need to make sure you get those in your book or on your paper or spread around on your desk. I'll give you 5 seconds to pause the video. All right, so hopefully you've now got your triangle hierarchy all fixed so that it's like mine. Now we are going to use that to answer the questions on the next page. Because once we do, this should be pretty easy. All right. Use the triangle hierarchy that we just did on page 246 to answer the questions. Name a category shown on the hierarchy, then name a subcategory of that category. So just quickly, let me throw that back up there. Now, triangles is one of our categories. It has a subcategory of isosceles triangles, and isosceles triangles is a category that has a subcategory of equilateral triangles. We can pick whatever we want. I'm going to use isosceles and equilateral for this one just because those are new terms, and I want you to become familiar with those. So I am going to say that one of our categories was isosceles triangles. Oh, come on, not again. and underneath isosceles triangles on our hierarchy was equilateral triangles. Okay? They would like us to draw an isosceles triangle. So the isosceles triangles were the ones that had 2 or 3 equal length sides. So really, I could draw any of these 3 or the 3 below it that were equilateral triangles. Because remember, equilateral triangles are a subcategory of isosceles, which means they share the same characteristics of isosceles triangles. But I'm not going to draw an equilateral triangle. I'm going to draw one of the 3 that couldn't filter down any farther or further than isosceles triangles. But really, I could draw any of these 3 down here as well. I'm just going to do this very first one here. I've already cut that one out and put it on my page, which is why they're simply saying draw. And this might not come out all... Well, actually, I'm going to cheat because I can. And it should look a little bit neater. All right, so I'm trying to draw that one. And I'm going to put the marks in case my drawing didn't come out so well. But there are the marks to show that, okay, it does have at least 2 equal sides. Part B, draw a triangle that is not an isosceles triangle. So again, I can't draw any of the 3 that were isosceles. I can't draw any of the 3 that filtered down to equilateral triangles because those are a subcategory of isosceles. I have to draw one of the triangles from up above at the top of the page. So I'm just going to draw this one right here. That way, if my drawing's not so good, the markings will clearly show that none of the 3 sides are equal, but really any of the ones that are up here would work. All right, maybe that drawing didn't come out quite as well, but 1, 2, and 3. So we can see the tally mark to show none of those sides are the same length, and to be isosceles, at least 2 of them would have had to match, and they don't. All right, problem 3. Draw an equilateral triangle. Now, there were only 3 of those. At the very bottom there. There we go. So I'm either going to draw this one, or this one. I'm just going to try to draw this first one to the best of my ability. You know what? Let's use the straight line because I can already see this is going to go poorly if I don't. Okay, so I tried to draw all 3 lines of the same length, but in case it's not obvious, that's what those tally marks are for. Let us know that each of those 3, whatever that measurement is, it's the same on all 3 sides. And again, we'll just ignore that. We'll pretend that didn't happen at all. All right, part B. Is your equilateral triangle also an isosceles triangle? There's a couple ways we can answer that. Well, not the first part. Yes, it is. It's how we could explain it. We could state that equilateral triangles are a subcategory of isosceles triangles. So, yep, they're the same. Or we could say equilateral triangles have at least 2 equal sides, kind of playing not off of the term isosceles, but off of the characteristics of it. So there's a couple ways you can say it, whatever makes sense to you. So is my equilateral triangle also isosceles? Yes. For my explanation, I'm just going to write it has 2 or more equal sides like an isosceles triangle. So again, if it matches the characteristics of an isosceles triangle, then it would also be called an isosceles triangle. And remember, pause the video whenever you need to if I'm going too fast. In each statement below, replace the underlined category with a different category from the triangle hierarchy so that the new statement is still true. All triangles have 3 sides and 3 angles. Okay? They want us to replace that. Well, triangle was the main category on our page, and it had subcategories below it, which means isosceles triangles and equilateral triangles would also have to have 3 sides and 3 angles, because how can you be an isosceles triangle if you're not a triangle? Now again, we can do isosceles or equilateral here. I'll just do isosceles. All isosceles triangles. But we could have put either term here. Part B. All isosceles triangles have at least 2 sides the same length. So if we look back on our hierarchy, there is a subcategory. Underneath isosceles triangles, we have equilateral triangles. All 3 sides are the same length. So if all 3 of your sides are the same length, then obviously at least 2 of them are the same, because 3 is more than 2. So that means we can say the same thing about equilateral triangles. They also have at least 2 sides the same length. Hopefully I can squeeze all of this in here. Equilateral triangles. Close, almost got it. So all isosceles triangles have at least 2 sides the same length. Equilateral triangles are a subcategory of isosceles triangles, so all equilateral triangles also have at least 2 sides the same length. All right, problem C. All isosceles triangles have a line of symmetry. Now, this is something that we haven't talked a lot about. You heard me mention it just a little bit ago. Symmetry, these are lines kind of like a mirror. If you could draw a line straight through the shape, one side would look like the other. And maybe some of you actually learned this trick back in kindergarten, 1st grade, maybe making Valentine's cards. If you fold the piece of paper in half and then draw half of the heart and then cut it out, then the other side, when you unfold the piece of paper, ends up matching. You've basically used symmetry to help you try to make a heart that looks symmetrical, both sides looking the same. So if isosceles triangles have a line of symmetry, this is what that would mean. Let me get my line tool out. Here's my set of isosceles triangles. I could draw a line right down the center of this one, and if we were to fold, like if this was a piece of paper and we folded right there, this part should cover this one perfectly, or within reason, as much as we can get perfect. For this one, I would have to draw across this way, and if I folded, this top piece would cover this bottom piece. And then this last one would be similar to that first one I did. And if you've ever made paper airplanes, you understand the importance of being able to fold so that the 2 wings make the same shape. That's kind of what we're looking at here. I didn't get that line quite perfect, but you get the idea. If we were to fold on that line, the 2 parts should cover each other well. So, back to this. All isosceles triangles have a line of symmetry, so all blank have a line of symmetry. Well, again, isosceles triangles have a subcategory called equilateral triangles. So any of the equilateral triangles should also have a line of symmetry. And I'll just do it on this one here, because I'm getting all these random lines all over the place. So we can see this side would end up matching that side. And again, we could do the same thing over here and over here. So if all isosceles triangles have a line of symmetry, then all equal, I guess I need the squiggly line, not the straight line maker. All equilateral triangles have a line of symmetry. Last question. Look at your answers to problem 4, the ones we just did. Describe any patterns that you see. Hint, think about categories and subcategories. Again, describe any patterns you see in our answers for problem 4. Give you a few seconds to think about that. All right, hopefully you've come up with something, or you paused the video to give yourself more time. The one thing that hopefully sticks out, and maybe it doesn't because maybe you've never heard of these terms before and you're still trying to absorb that. In our hierarchy, the page to the left, underneath triangles, we had the subcategory isosceles triangles. Under isosceles triangles, we had the subcategory equilateral. And then here again, we see isosceles equilateral. So there's a pattern. Maybe you noticed something else, but when they ask us to describe it, I'm going to say that each answer that we had to write was a subcategory of the category above it. So again, the answer to A, isosceles, was right underneath the category triangles on that page to the left. Our answer to B, equilateral triangles, that was right below isosceles triangles on that page. And for C, equilateral triangles, again, was right below isosceles on that page. So if we were to have another question, all we'd really have to do is, what was the underlined part? Look at that page to the left, and what was the subcategory directly below it, and that would be our answer. All right, that is the end of that page. So let me go ahead and turn the book to the last page in this lesson, the math boxes. Hopefully everyone is trying the math boxes, or at least watching as I do them. Again, we don't usually get a chance to do these in class very often, but they are important because they are a review of everything that we have done in the past. Not to mention that they also are a preview of things that are going to be seen again. All right, lesson 7.5. So we can get that squared up a little bit better. All right, here we go. Math boxes. Problem 1. Find the area of the rectangle. All right, first thing, area equals length times width. Now, in the beginning of the year, we would count squares, but once we start getting different size pieces, we have 3 different size pieces here. So counting squares, probably not going to be the best way for this, but you could make it work. So I'm going to simply multiply my length by my width. So my length is 5 1/4. It's a beautiful 5. And my width is 4 1/2. And whenever I have 2 mixed numbers where that means there's a fraction involved, I like to use the improper fraction method for multiplying, or the fraction method. I call it improper because you end up making fractions that normally you wouldn't want to make, or at least you wouldn't want to leave in an answer. If I'm not seeing 2 fractions pop up, then I like to use the partial product. So in these past lessons, if you've seen me go back and forth and you're wondering why, it's just like you. There are some things you've learned tricks for and other things you haven't. Certain things that you found an easier way to do or makes more sense to you. And this is just the way it makes sense to me. And if nothing else, at least you see different ways of multiplying with mixed numbers. So the first thing I'm going to do is turn 5 1/4 into an improper fraction. And again, I could draw 5 circles, cut them all into fourths. I'll do it really small. And if I cut all of these into fourths, and I counted them all up, okay, well, that has 4 pieces, that has 4 pieces. I am getting 5 groups of 4. All of these would have 4 pieces. So that's really just 5 times 4. There's my 5 times 4. But I also would have had to draw that 1/4. That one part of the 4 out of the 4 that would still be there. So when I'm done, I'd have to then, after I multiplied my 5 groups of 4, I'd have to then add this one piece. And there it is. So 5 times 4 is 20, plus that one piece I had to start with is 21. So I get 21/4. And I'm going to do the same thing here. 4 times 2 is 8, plus the piece that was there to start with. 8 plus 1 is 9. I get 9/2. All right, now we're going to go ahead and multiply. Let's start with the easy part. 4 times 2 is 8. 21 times 9. I would bet some of you could do this one in your head, but just to be safe. 9 times 1 is 9. 9 times 2 is 18. I get 189. Now, this, I guess, would be the one negative of using this method. I always get a division problem at the end. I mean, maybe not always, but usually I'm going to get a division problem at the end. Had I used the partial products method, I usually get 3 different sized fractions. And then I've got to convert those to something with a common denominator so I can then add those. And then there's a chance that they're an improper fraction and I have to divide anyway. So I would rather just divide and be done with it and not have to deal with all those fractions with unlike denominators. So I'll have to decide somewhere we need to divide 189 by 8. All right, 8 cannot go into 1. It can go into 18. 8, 16, 24 would be too much, so it can only go into 18 twice. 8 times 2 is 16. Bring down the next number and repeat. See how many times 8 can go into 29. 8, 16, 24, 32 would be too big, so it can only go into it 3 times. 8, 16, 24. And 29 minus 24 is 5. Nothing left to bring down, so that 5 becomes our numerator. And we are dividing by 8 in this problem. So our area ends up being 23 and 5/8. And we are doing centimeters. So centimeters times centimeters is centimeters to the 2nd power. Or if you want to write out square centimeters. So what was the number model we did? Again, I always hate it when they put it down below because if we didn't know the problem to do, we couldn't have ever found this in the first place. But anyway, the problem we did was 5 1/4. That was our length. We multiplied by 4 1/2. That was our width. And I'm just going to do R for rectangle. Use whatever variable you want. All right, problem number 2. 1/7 times 8/9. This is nice and easy. When multiplying fractions, you have to have fractions. We do, so now we multiply the numerators. 1 times 8 is 8. Now the denominator, 7 times 9 is 63. And it's not an improper fraction, so we're done. All right, part B. 6 times 3 is 18. 11 times 4 is 44. Not an improper fraction, so we're done. I'm going to show this next step just to kind of get you used to the future. A lot of you during the course of the year were starting to reduce or simplify. And I told you, don't worry about that now. We're really just worried about making sure we know how to multiply with fractions. But you're going to have to start reducing. 18 and 44, you should recognize these are both even numbers, which means both of them can be divided by 2. 18 divided by 2 is 9. And we can check our work. 9 times 2 would be 18. 44 divided by 2 would be 22. 22 times 2 is 44. It's not going to be able to be reduced any further than that. But our final answer would be 922 in the future. For us, right now, 18/44. All right, problem 3. Use an estimate to place the decimal point. The correct digits are given. So we have seen this before. When we first started learning how to multiply, where do we put the decimal? Do we just drop it down like when we add or subtract? Do we bump it up like when we're dividing? No, we do not. So we learned a couple methods. This was the first one. So the first thing we're going to do is we're going to estimate. So for 2 3/10, I imagine most of us would just say 2. And depending, 158 6/10, some of you might round this up to 160. But I would imagine more of you would probably rather deal with 15 than 16. I bet a lot of you know what 15 plus 15 would be, because that'd be 15 times 2. 2 times 15 would be 30. And then we have a 0 at the end. So 30 with 1 power 10 at the end there. We're estimating somewhere around 300. Had you rounded up to 160, you would have had an estimate of 320. And now we're supposed to use that to place our decimal. When we put the decimal here, our answer is a little bit bigger than 3. Now it's 36 and change. Now it's 364, at least it's in the 300s. Now we're closer to 4,000. And then we just get further and further away. So the only spot that really seems close to our estimate is right there, 364 and 7/800ths. Question 4. Fill in each blank with less than, greater than, or equals. Remember, the tip of the arrow, that's the number that's smaller. The wider spacing, or the mouth, that's the larger value. So for 12 times 1/3, we shouldn't need to multiply this. I will, but we shouldn't need to. 12 times 1 is 12. 1 times 3 is 3. 12 divided by 3, 3, 6, 9, 12, is 4. So all of this right here really just means 4. So this is 4. Over here we have 12. 4 is smaller than 12. Now here's why we shouldn't have had to do that. We should all remember that when you multiply by 1, you get the same answer. Whatever was here times 1 stays the same. If the number is larger than 1, whatever you multiply, if it's more than 1, then you get a larger answer than what you started with. And if you multiply a number by something smaller than 1, you get a smaller answer than the number you started with. Well, we're starting with 12, and there we see the 12. 1/3. It doesn't equal 1. It's not bigger than 1. It's smaller than 1. So anything times less than 1 is going to give you a smaller answer. So down here, 2/3, 2/3. For those things to be equal, whatever we multiply has to equal 1. If 8/8 is bigger than 1, then we know this is going to be bigger than 2/3. If 8/8 is less than 1, we know that this side is now going to be less than 2/3. 8 divided by 8 is 1. Anything times 1 stays the same. So these will be equal. And then the last one, 1 3/8. We see 1 3/8 over here. So it's just a question of, is 6/5 equal to 1? And these end up being equal. Is 6/5 bigger than 1? And then this side is larger. Or is 6/5 less than 1? And this side is then smaller. 6 divided by 5. 5 can go into 6. 5 times 1 is 5. We get 1 left over, nothing to bring down. It's not much bigger than 1, but 6/5 is bigger than 1. So anytime you multiply a number by something larger than 1, you're going to get a larger answer. So this side is going to be larger than 1 3/8. All right, last question on the page. Explain how you solved problem 2b. All right, so 2b was 6/11 times 3/4. I'm just going to write it over here so I don't forget. All right. I'll say first, I multiplied the numerators to get the numerator in the product. Remember, the product is the answer to a multiplication problem. So I'll put in parentheses 6 times 3. That gave us the 18. That's where the 18 came from in our final answer. Then I multiplied the denominators. To get the denominator. In my product. And in parentheses, that was the 11 times 4. That's where we got the 44. All right, so that's where we got the 18 for the numerator position. That's where we got the 44. And I guess we wanted to, the final answer was 18 over 44. All right, class, that is the end of lesson 7.5. Hopefully you paused when you needed to, tried some of it on your own when you thought you had the hang of it, and hopefully everything went well. If for some reason, again, that you think I've made a mistake anywhere, feel free to email me. Or if you have any suggestions, you can't comment to the video because it's set to be made for kids. So the only way you can really let me know is if you email me at the school email or give me a call. You've got my phone number on those cover letters as well. Whatever works best for you. All right. I hope everyone's having a good day. Bye.